The purpose of this lab is predicting the behavior of DC circuits with resistors in series by making calculations based on ideal models, employing multimeters to measure actual values of current and potential differences in the circuit, and examining the behavior of an RC circuit by measuring the charge and discharge times of an ohmic capacitor. The main physical principles involved in this lab are the energy conservation and charge conservation principles, as well as Ohm's law and RC circuit equations. The current on a DC circuit with 2 resistors and 1 battery was measured and with an ammeter and fell well within 10% error. Similarly, the potential differences across components was recorded and the resistance of each component was calculated and was found to be within reasonable tolerance of the manufacturer provided values. The charge and discharge times of an RC circuit were measured. These times did not align with the expected trends. The DC circuit considered in this experiment consisted of 2 1.5 volt batteries, 2 resistors of 147 ohms, and 2 ammeters. The system were the tools used to measure current and potential difference, and the surroundings were the circuit, including other elements through which there is a current and potential difference. The circuit is in series. Thus, by Kirchhoff's junction rule, the charge should be conserved. Considering that the ammeters have zero resistance, the batteries have no internal resistance, and the wires have no resistance, the loop equation for the circuit is: applying Ohm's law, the current I in the circuit is estimated to be 20.41 milliamp. The current on the ammeters was measured to be of 19.1 milliamperes. The percent error associated with this measurement is thus 7%. When reversing the connections to one of the ammeters, the current registered by this ammeter is minus 19.1 milliamperes. This is because the current is flowing in the direction of the electron flow instead of in the direction of conventional current established by the ammeter's positive and negative. An ideal voltmeter has infinite resistance, hence the current flowing through a voltmeter in series is 0 amperes. Thus, the circuit is open and no current flows through the ammeter. The potential differences were measured across the circuit elements with 1 ammeter. By applying Ohm's law, the resistance of each component was calculated. Now, a second experiment is considered with a circuit consisting of a 14 ohm light bulb and a 1 Faraday capacitor connected to 2 1.5 volt batteries. When the circuit is closed with the battery connected, the bulb becomes bright until the capacitor becomes fully charged when current stops going through the circuit. Likewise, the capacitor can be then connected to a light bulb and it will become bright and then dim again when the potential difference across the capacitor is low. The capacitor was fully charged and then fully discharged. The charge and discharge times were estimated to be 14.8 seconds and 13.5 seconds. Likewise, the experiment was repeated for a circuit with an additional 14 ohm battery. The charge and discharge times were 21.3 seconds and 20.5 seconds. In this case, the charge and discharge times should be double with respect with the other circuit, and also the charge and discharge times should be closer to each other, so that means there is error in the measurements. For the last experiment, the circuit was simulated with FET's AC circuit lab. A 30 ohm light bulb was connected to a 1200 mFaraday capacitor. The capacitor was charged with a 3 volt battery. When charged, the battery was disconnected and the circuit was closed. The voltage across the capacitor plates was recorded against time until the capacitor was fully discharged. The voltage difference across the capacitor's plates should vary according to the following equation. Rearranging the equation and taking the natural logarithm, we get the following equation. Thus, by measuring the change in voltage across the capacitor against time, we can obtain an estimate for the time constant RC by estimating the slope of the plot of the natural logarithm of the potential difference divided by the original potential difference against time. The following values were obtained and plotted. The value for time constant measured from the plot was 5.94, whilst the calculated value for time constant was 6. Some errors include that in real life the ammeters are not ideal and they have resistance, and the same occurs with wires. Furthermore, the internal resistance of the battery is not accounted for, and this causes errors in the calculations. The components of the circuits have values for resistance and voltage provided by the manufacturer, but this fall within the fault tolerance range and are not exact, causing errors. When measuring the charge and discharge times, it was assumed that the circuit was charged and discharged when the light became dim. However, at this time, there still might be current in the circuit, but the power from the bulb converted to the light is too small for it to be visible. If the capacitor was charged in a circuit with no resistance, the time constant would tend to infinity. This would make the charge on the capacitor independent of time. The capacitor should become charged instantly. Considering that the wires have a very small but non-zero resistance and due to material properties and other imperfections of the capacitor, if we were to connect the capacitor to the battery and measure the charge in the capacitor, we would see that it would take some time to fully charge. A DC circuit with 2 resistors and a 3 volt battery was set up. Through some experimental measurements, the current in the circuit was recorded and the resistance of the components was estimated through the potential difference measurements. The experimental measurements fall well within 10% error with respect to the theoretical calculations due to component imperfections and tolerance. An RC circuit was set up with light bulbs, a battery, and a capacitor. The charge and discharge times were measured with 1 and 2 light bulbs by observing the light emitted. The measured times did not follow the expected trends, which could be due to the experimental errors described. Finally, a simulation of an RC circuit with a capacitor and a light bulb was set up. By measuring the potential difference across the capacitor and recording the time of the measurements, the time constant of the capacitor was estimated by taking the slope of a curve based on the mathematical model presented. The result closely agrees with the calculated time constant for the capacitor.